When I first introduced the heat equation, the one-dimensional heat equation, I said it's surrounded by some insulation, and then the two endpoints are touching ice, so that the boundary conditions say it's 0 degrees Celsius at the end. Now you might question what happens if there is no insulation. Let's say this is air. And then, I mean, there might be some thin coating around so that the heat loss is not like very fast. It might be losing a little bit, little by little. And in such a case, you have something called Newton's law of cooling. So if you have any, let's say you have any object in an ambient space, then if the temperature of the object is T and the ambient temperature is A, then the difference between the ambient temperature with the temperature of the object should determine how fast the temperature would change, right? So, for example, if this object was a cold cup that's like 0 degrees Celsius and the room temperature was 20 degrees Celsius, then the difference between the two is positive, so you know that the cup would be rising in temperature. Okay? On the other hand, if this was coffee, which is hot, then it will be hotter than the ambient temperature, so that the difference will be negative. So you see that the temperature of the object should go down. Okay? And such an idea is called Newton's law of cooling. Here I wrote down not alpha, but it's proportional. So the rate of change of the temperature of the object should be proportional to the difference between the ambient temperature and the temperature of the object. So you can kind of see that similar things should be happening here. And for the sake of simplicity, let's just say that the air is cold. The air is also 0 degrees Celsius. Okay? And then if you apply the Newton's law of cooling, in this question we have the UXT as the temperature of the object at location X, right? And if you think about the lateral action, you can say that this should be proportional to 0 minus u, right? Which means that t derivative with respect to u should be proportional to 0 minus u, so that the usual heat equation, which was ut equals to k times uxx, would now have an extra component, which is, let's just call this other coefficient as beta, and it will be like negative beta u because of this minus. Okay. Now, if you leave this iron bar not in a 0 degrees Celsius environment, but let's say you have some, if you say this is like 20 degrees, that's the usual room temperature. That I think 20 degrees is something like 70 degrees Celsius, Fahrenheit or something. Okay, so you do 20 minus u and then plus beta. That will be a more reasonable kind of differential equation. But if you do that, then it becomes really hard trying to deal with this. This requires something called eigenfunction expansion. So let's just do the easiest case where this is simply minus beta times u. And I want to show you how this can be done in this example problem where k is set as 0.4 and beta is set as 0.2. Okay. But the method I'm showing you should work for any generic k and beta. Now in your homework problem, I'm going to, well, you'll try to work out that if you do the change of variables, say uxt equals to e to the negative beta t times wxt, then this basically transforms the problem into the usual Hit equation. But that's for you to try out. I'll just try to use the regular separation of variables to solve this, all right? So, solution. What do we start with? Let's see if you know separation of variables. What do you do? uxt is?
xxt.
xxtt. And you're looking for the building blocks of the solutions to eventually match with the initial conditions. But for now, we're only looking for solutions that satisfy the first two, with the form being function of x times function of t. And we will then later take linear combinations of all the functions, and then this will come into play after. So we plug that into the left side. Because this is differentiated by t, the left side has xx t prime of t. Here you have two derivatives in x, so this will be differentiated twice. And then here there's no derivative, so it's just this by itself. Okay. And then what should I do? Divide both sides by?
kxt.
Yeah. So we divide everything by k times x times t. K is 0.4, so we're going to divide everything by 0.4. X t. This is really x of x and t of t. I hope you're okay with it. So this x and this x will cancel out. This t and this t will cancel out, and here both of them cancels out. And the resulting equation is that you have t prime over 0.4t equals to just x double prime over x, and then 0.2 divided by 0.4 is like 1/2, right? Or yeah, let's just put 1/2. Okay. Now we used to just call this. Well, the next argument is that the left side is a function of t and the right side is a function of x. Therefore, for them to be equal, they have to equal as a constant. And we used to name this as negative lambda because then you get a very recognizable problem in Sturm-Liouville problem, right? But here, what we are going to do is we're just going to call it mu. Because it's not really lambda, you'll see. And then the boundary conditions, these two conditions imply that x of 0 of t of t equal to 0 and x of 4 t of t equal to 0 since t of t equals to 0 would give you a trivial solution. We have x of 0 equals to 0 and x of 4 equals to 0. Okay. So that's what we get from the boundary conditions. Then let's solve this for x double prime by first adding negative 1/2 to the other side, so that you have x double prime over x equals to mu plus 1/2 multiplied by x, so you get x double prime equals to mu plus 1/2 times x. Move this to the left side and you get x double prime minus mu plus 1/2 x equal to 0. So you get this equation with these boundary conditions, which would be very familiar if this was instead of lambda. So what we're going to do is we're just going to say lambda is negative mu plus 1/2, so that we get our Sturm-Liouville equations. This with the endpoints as these, and we've solved these questions so many times, we kind of know immediately what these solutions should be. Like, what are functions that have endpoint 0? Sine or cosine?
Sine.
Sine, right? So, see, sine graph goes like that. So, from the two endpoints, it becomes 0. Right? On the other hand, cosine graphs, they go like this from 0 to pi. So, the value itself is not 0 for the cosine, but their derivatives are 0. So, if you have a Sturm-Liouville problem that's simple like this one, for a simple one, like that one, with the endpoint value equals to 0, you know it should be the sine functions. If the derivatives are equal to 0, then you should go for the cosine ones, right? Even without working it out, you should know, right? Okay, so what we get here is that eventually, if we work out the Sturm-Liouville, then we will get that x should be the sine functions n pi over 4x. So if you want any non-trivial solution of this condition, it must be some non-zero constant multiple of the sine n pi over 4x, with some n being some integer, positive integer. And such solutions will only exist for lambda values equal to what?
N squared pi squared.
Yeah, n squared pi squared
16
over 16. And now you eventually want to use that to solve for t. But look, mu is not lambda. See, negative mu minus 1/2 is lambda. So if you move the negative mu here, put the lambda to the other side.
should be 1/2 minus.
Right. So mu would be negative n squared pi squared over 16 plus 1/2. Okay. Is that right?
No. It's minus 1/2 because.
No, I put a parenthesis, right?
No,
Let's see. Okay, let's see. What is it? Lambda equals to negative mu minus 1/2.
Oh, yeah.
Move this, move that, so it's mu equals to negative lambda minus 1/2, and then you pull the minus out, that's what you get.
Yeah.
So mu is negative lambda plus 1/2, but lambda is this, so that's what you get, okay? All right, so we're very close to figuring out what x and t are. We already figured out what x must be. Now we have to figure out what t of t is, and t of t satisfies this equation. This equals to mu. And let's erase this portion. And just rewrite what it means for this equal to mu. If you move this to the other side, the equation that you get is t prime equals to 0.4 mu t, where mu is a constant, right? And you just have to remember from ODE class that if you have y prime equals to some constant times y, what's the solution in general? Y equals to?
e to the
I don't like c, let's say a, okay? So if it's y prime equals to ay, then it must be e to the at, right?
yeah.
With some constant c. Okay, that's the general solution. you can just plug this in to see that it works, or if you are not happy with it, you can always divide by y both sides and integrate both sides, because y prime over y integrates to ln of y. You know that, right? Y prime over y integrates to ln of y. The right side becomes at, and then if you solve for y, you get exactly this. Okay? So I will pretend that everyone knows this fact, so that from here you get this, and that immediately says that t would be t of t would be some constant times e to 0.4 mu t. But since we have the mu value there, well, 0.4 is 4 over 10. So let's see, if you multiply 4 over 10, 4 and 4, 16 reduces to just 4, so you're going to get t of t equals to some constant times e, so negative n squared pi squared over 40, and then half of 0.4 is 0.2, right? So it'll be plus, I'll write 1/5, but you can write 0.2. So that's what you get as your t of t. Okay. So this is step 1, okay? Step 1, we figured out what x of x is and what t of t is. Now you get u of xt as this function times sine. And since we've figured out the building blocks, now what do? You take linear combinations of them, meaning that you add them up, every one of them. Okay? So in general, you see that u xt summation n equals to 1 through infinity of Cn e to the negative n squared pi squared over 40 plus 1/5 t times sine n pi over 4x. In general, this would satisfy both the heat equation and the boundary conditions. Okay? And it's a good exercise to convince yourself that it's true by actually plugging this in. If you plug in, for example, 0 here, what's sine of 0? 0. So u of 0t would be 0. Do you agree? Right. If you plug in 4 into x, you get sine n pi. What's sine n pi?
0.
So this is again satisfied. And then the other one's a bit more tricky, but if you, oh, sorry, this should be t outside. If you differentiate by t, this would come in front, right? And then if you differentiate twice by sine, then it will be negative sine with n squared pi squared over 16 being in front. And then you have to think about what happens. And actually, yeah, I think eventually you'll see that the two sides are equal if you do that. Okay. So that's step 1. What's the next step?
Use the last condition.
Yeah, now you use the initial condition, right? You set, you plug in 0 for t. If you plug in 0 into t, then e to 0th power is 1. So you end up with summation from 1 through infinity of Cn sine n pi over 4. X is what you get from this equation. However, we want that to equal to x, right? So we want this to equal to x. What's that? That's trying to express x as sums of sine n pi over 4x. That's called the Fourier sine series, right? Yeah. The Fourier sine series has the formula that Bn is equal to 2 over L, 0 to L, x times sine n pi over 4 x dx. Okay. So you can do this calculation, and let me see. In our case, L is 4. This is also L, but that's 4. integrate, you get cosine over pi. Let's do it. I wanted to skip this step. Can't. D integral x differentiates to 1, differentiates to 0, sine n pi over 4x. Integrating that gives you negative n pi over 4 cosine of n pi over 4x.
Does it mean the other way around?
Oh, sorry.
No, it's
4 over n pi
Yeah.
should be the reciprocal, right? Okay. And then you integrate one more time, you get the sine, but you know, from our experience, the sines don't give you anything. So the only thing that would give you something that's non-zero would be this one. So 2 over 4 is 1/2, so we're going to get 1/2 times negative 4x over n pi cosine n pi over 4x, and to this we're plugging in 4 and 0. And when you plug in 0, 0 going to x doesn't give you anything at all, right? However, if you plug in 4 into x, that's negative 16 divided by 2, so it's negative 8 over n pi, negative 1 to the nth power, because cosine n pi is negative 1 to the nth power. Is this okay? Are you?
Why does it go to negative cosine and not positive?
Oh, because cosine differentiates to negative sine, right?
Yeah.
So if you integrate sine, you get negative cosine.
Oh,
Yeah.
okay.
You know, it's really easy to confuse between the two. The sine integrates to positive cosine. One thing that you can use is, if you look at the graph of sine, it's increasing, right? So if you differentiate sine, you're going to get positive. Right? Whereas if you look at the cosine graph goes like that. It's decreasing. So if you differentiate cosine, you should be getting a negative. Okay, that's how you remember that. And then you have to remember that since you're integrating, the signs will be opposite of what you get from the differentiation. Okay, so anyways, we get that, and then finally, because this is the Cn, same thing as the Cn, right? So now we can say that this is indeed Cn, then plug in this to here, and now we have the final answer, which is mu xt equals the summation of n equals to 1 through infinity of negative 8 over n pi, negative 1 to the nth power, e to the negative n squared pi squared over 40 plus 1/5 times t, and then sine n pi over 4x. Okay, now you might wonder how this compares with the usual heat equation. So if you were to solve the heat equation without this part here, then what you're going to see is that you get exactly the same thing, except that I'm not so sure about this one. I think it's still the same. Yeah. So you just have 1/5 missing. So what it means is that because there's a heat loss in the lateral direction, it just goes to 0 much faster. Now the really strange case would be when you have the ambient temperature not at 0, which is different from the boundary conditions. Then you might have like the center of the bar increasing in heat to the ambient temperature, which is 20 degrees Celsius, whereas the boundary being ice, which is here. That's much more complicated. It's not as simple as this one. But I thought this is a good example of how you can do separation of variables for other cases as well.